Hello, everyone, and welcome to another lecture for Auto 105 Manual Powertrains. Today, we're going to talk about Chapter 8, which is our first chapter getting into talking about differentials. We're primarily going to be talking about differential technology and open differentials. We will have two lectures, Chapter 9 on mechanical limited slip differentials, and then Chapter 11 on electronic limited slip differentials. So we're going to briefly touch on it here, but for all intents and purposes, what we're talking about right now is just the differential in an open state, and we'll get into what I'm talking about with what's open, what's locking, what's limited slip, so on and so forth. But what we're looking at is the final drive or final gear ratio change in most cases. Yes, there are some vehicles out there like a Unimog and a Humvee that do have a portal box for the axle. What that does, that allows the axle shaft to sit higher than the actual wheel, so you get better ground clearance, and you can have an additional low range in that portal box. But those are very, very rare occasions that you'll see that. For the most part, you're going to see the final drive differential being the last bit of torque multiplication that we're going to have before the torque of the engine gets down to the wheels. And in a differential, it will always be torque multiplication. Our gear ratio will always be underdriven in a diff. It will not be overdriven. The vehicle wouldn't move if that was the case. But we're going to look at all the different components that are involved with that. Now, we do have a final drive differential and a transaxle that will operate with the same carrier assembly and the same ring gear assembly, but we're going to have a different design and gear. Typically, it's going to be a helical gear for the ring gear and for the drive pinion gear. So it's relatively the same. For what we're talking about in this chapter, we're talking about differentials that are separate from the transmission itself. So nothing that's going to be a transaxle. So either rear-wheel drive or four-wheel drive applications. We're going to have the ratio is a set number. There are older or heavy-duty diffs that would be two-speed diffs. You'd have a high and a low range, and that would change the drive pinion. The ring gear would stay the same, but we'd change the drive pinion. And so in a case where like you were going up a really steep hill, you'd have to get out normally to do this. You'd have to get out or you'd have mechanical linkage. You would shift the rear end into low, go up the steep hill. Once you get to the top, then you would switch the diff back into high, and you do most of your driving in high rear gear. As I stated before, our rear gear ratio will always be underdriven, and the ratio range that we can be pretty vast. We can be as high as 2.5 to 1 ratio and as low as almost 6 to 1. The lowest I've really seen is 581, 588 to 1 rear gear. The lower the ratio, obviously, the more torque multiplication we're going to get. Oftentimes, when we look at our ring and pinion set, it will be stamped on the ring gear itself. So if we look at our picture right here, I have 11 and 41. The 11 is the indication for the amount of teeth on the pinion gear. That will be our input. And 41 is the amount of teeth on our ring gear, and that will be our output. So we divide our output by our input. And in this case, we're getting 4.1 ratio. So that means that the pinion gear is turning 4.1 full rotations for one rotation of our ring gear, and we're multiplying any torque we have by 4.1. So if we have 100 foot-pounds of torque coming out of the transmission and going into the diff, it's being multiplied by 4.1 to be 410 foot-pounds that is going down to the wheels and moving the vehicle. So we're going to get a significant amount of increase in torque from these gear ratios. Oddly enough, I get a lot of students asking me like, how can they increase power? How can they make their vehicle, have more horsepower? And the reality is if you want to have like a quantitative, you will feel it modification, it's changing your rear gear. So if you're, for instance, if you have like 293 rear gears because your car is meant for getting better gas mileage, and you were to put 373s in it, you will notice a difference, and it will be every single time you will notice a difference. Now, the downside is the lower the ratio, the reduced top speed you'll have. So you'll be operating the engine in a higher RPM, and you won't be able to travel as fast. The higher the ratio, the greater your overall top speed is going to be. So that is something that you do kind of need to, find a happy median, and you do need to be honest with yourself on how the vehicle is being driven. Is the vehicle being driven on the freeway, or is it being driven in a way that we will be able to have it be, have a whole ton of acceleration and be fun and peppy to drive? Another thing that we'll have as part of most rear differentials is going to be a tone wheel for the ABS sensor. A lot of solid axle rear wheel drive vehicles will have one speed sensor, and it will be located on the rear diff carrier assembly right next to the ring gear. And that's what you have photoed right here. So that will be something that is going to be required to be changed out if we do a diff overhaul, and may or may not need to be inspected anytime we are working on the differential. Our gear design that we're going to have for our ring and pinion is going to be called a hypoid gear set. Now, these hypoid bevel gear sets, what they do is they help reduce the height of the drive shaft tunnel, meaning that we don't have to have this super high drive shaft tunnel going through the entire middle of the vehicle, so we can have a bench seat in the rear effectively. It also allows for quieter rotation because the gears are cut at an angle, and it also gives a great amount of surface area, so they're very, very strong. Now, they are less fuel efficient than standard spiral gears, but because of their added strength and the torque multiplication that they're going to be under, it is important that we make sure that we are having these in proper operation. This will require us to have much heavier gear oil. So you're looking at the gear oil for this particular diff being 80W90. They can go as much as 75-140. And that is so that we can have that tension and allow for, or the hypertension of the fluid against the gear, so we don't shear any of the fluid off, and we have plenty of lubrication as the diff operates. So as the differential is operating, it's not only multiplying the torque that's coming out of the transmission output before it goes down to the drive wheels, but it also has to give us the ability to navigate around a corner and allow for the wheels to turn at different rates. When a vehicle travels around a corner, either left or right, it doesn't matter, we're going to have different rotational speeds of each wheel. So the inner wheel on a turn is always going to turn slower and travel less distance than the outer wheel. The outer wheel will always spin faster because it is having to travel a greater distance. The arc that they're going to be turning on is much greater in that point. Most differentials, as we're going to talk about in this particular chapter lecture, are going to be open differentials, meaning that they will allow for unimpeded movement of the left and right axle independently of themselves to allow for the smoothest operation to go around a corner. Now, you can limit that and prevent a slip to occur with a limited slip differential. The problem with an open differential is if we get into a situation where one tire is in an area where there's not any traction, in a muddy puddle or like sand or something like that, it will send all the torque to the wheel that's spinning free, and the wheel that is not spinning free will have no torque going to it because it is effectively bound up against the ground. So a limited slip prevents that from happening. It will allow for some slip around corners, but it will limit how much it will be able to get so that both wheels will turn with engine torque. And then the final method is going to be a locking differential, where you physically lock the differential in place and you have both axles turning at the exact same rate. If the axle is locked and you're going around corner, especially on hard surfaces, the vehicle is going to hop and chatter around. So it's not ideal in all situations. And we'll get into greater detail on limited slips and locking differentials in a later couple of lectures. Our open differential carrier consists of a couple different pieces, though. Our differential carrier case is going to house all of our gears internal to it, as well as the ring gear will attach to it. So our internal gears is we're going to have two side gears, a left and right side gear that will spline onto the left and right axle shaft, and then we will have a set of pinion gears. Now, these pinion gears are going to be the input going into driving the side gears, and the combination of these four gears allows for the different rotational speed of each axle shaft when going around a corner. The pinion gears will be held in with a pinion shaft on the differential carrier assembly, and they will be allowed to spin freely, but they will transfer their movement to the side gears. And if there is a situation where a vehicle is turning, they can spin opposite themselves and they spin independently. These systems can also be known, or the system of gears can also be known as spider gears, is the other term, because they kind of walk around each other. Now, it is a little bit confusing. We do have two sets of pinion gears. And in terms of a rear differential, we have a pinion input gear that goes along with a ring and pinion, and then we have pinion gears inside of the carrier assembly. I will do my best to not get those mixed up, to not confuse you any more than I probably already am. Now, the one thing that is the set thing with both sets of pinion gears is the pinion gear for the ring and pinion set and the pinion gears for the carrier assembly. Those are our input. So the pinion gear is directly turned by the drive shaft that's being turned by the transmission, and that turns our ring gear. Our ring gear is bolted to the carrier assembly. So our ring gear being the output, and then the pinion gears inside of the carrier, allowing for that free movement or the input to the side gears to allow the vehicle to move down the road. The side gears are as well splined to each axle shaft. They will be the last support for a semi-floating and a three-quarter floating type rear differential assembly. And we'll get into that here in a couple slides. Now, anytime we have gears operating against themselves, there's a couple things that we have to have in place. One is the correct amount of backlash. Backlash is the movement in between the contact points of both toothed gears. We need to limit the amount of backlash we have, because if we have too much, we can have the gears chatter and not have full contact and eventually break. If we have too little, it will bind the gears up and they won't be able to rotate smoothly. So backlash is one of those key kind of things that we're looking to make sure that we have dialed in anytime we're doing a diff overhaul or a diff repair. Backlash is adjusted in two different ways on differentials. We can either have a screw-in collar, like what you see on the top right photo there, where a collar is going to not only provide preload to the tapered roller bearings on the side carrier, and it's going to physically move the position of the ring gear in relationship to the pinion gear to allow for either to increase or decrease backlash. The other method that we can have is we can have shims. You'll have thick cast iron shims that get tapped in between the bearing outer race for the side carrier bearings and the differential housing. What this allows for is this allows for us to put tension on the bearings to allow for preload, but also to, again, physically move that ring gear into the pinion gear to either increase or decrease the amount of backlash that we have based off of what type of shin pack we're using. Personally, the adjustable collars are by far the way to go. You don't have a choice with it. Just heads up, you can't like modify one to be the other. But they are much easier to work on because you can really fine tune your adjustments. It's where shims are kind of a pain in the butt. I'm sure all of you are probably familiar with my giant bucket of disc shims. Well, that's where the application of where those metal discs fall in line. So let's look at an overview of all the components and how they are going to interact with each other, and then how they interact when we have a left and right turn. So our input into the differential assembly is going to be our large pinion gear. That's the one shaped like a cone, and it will be directly attached to the drive shaft. That will be in direct contact and constant mesh with our ring gear. Our ring gear will be attached to the planet carrier, and that will allow for the internal gears to allow for movement of the axle shafts at different speeds. So our drive pinion gears, those will be pinned to the carrier assembly and will rotate with the carrier assembly as the differential is turning. The side gears, those will be splined directly to the axle shaft. Now, in a straight application, we're typically going to have the torque going equally to both the left and the right. However, I want to make something a little bit clear here. Because our pinion gear, our large pinion gear, our input gear, is having to operate on the ring gear in an offset manner and not hitting it square on, we will have different length axle shafts. On average, a differential's difference in length is going to be about 3 3/4 of an inch from one axle side shaft to the other. So what that then causes is when you're going straight, it will still send torque and bias to the shorter axle shaft because it's less momentum and less effort to get the torque down to the wheels. I counteracted that when I built my 64 Ford by offsetting the differential 3 3/4 to one side so that both axle shafts are the exact same length. And theoretically, the torque will go equally to the right and left side as long as I'm not turning. I do have a limited slip in the back of that truck, but it's straight from the junkyard with no refresh in it. I am very suspect that it is pretty tired and probably is not limiting any slip whatsoever. But I digress. We went on a fun little tangent. When we're turning to the left, as we turn to the left, our planet carrier will then allow for the left side to spin at a slower RPM, and our right side will spin at a faster RPM, and our torque from our engine will be applied to that right side. The opposite happens when we're turning to the right. The left side gear gets the majority of the torque, while the right side one gets less because it is rotating slower and allowing the tire to rotate at a less RPM. Now, the axle housing itself can be made from a couple different types of methods. One method is where you make it all out of sheet metal. You bend it, weld it together, and then you have a removable center carrier. So a Ford 9-inch rear axle is like that, and most all Toyota and Nissan differentials are like that as well. But we can also have to where we can have a cast iron center that will have an interference fit of the axle tubes being pressed in the right and left side, and then those will be arc welded together. The either differential is both, they're both strong and they both will support the carrier assembly and the gear set. But it really kind of depends on what the manufacturer calls for in terms of their ability to change differentials out, their manufacturing process, so on and so forth. Now, the carrier assembly in these differentials for those sheet metal made housings, it is removable, meaning that the entire gear train can be removed once the axle shafts are removed. If it's the cast iron design, they're integral to the case, and you actually have to assemble everything inside of the case. So the ring gear is attached to the carrier, and the carrier gets bolted into the differential assembly, and the pinion gear is attached and supported by the bearings inside the housing before we even get the carrier in. The strength of our differential is going to be dictated off of a couple things. The axle's diameter and spline count is going to be one key factor, but the amount of torque that can be inputted to a differential is often going to be representative on how big the diameter of our ring gear is. So on the photo that we have here, we have that represented with a GM 7.2 on the left and a 8.5 rear diff on the right of the screen. The greater the diameter, the greater the tooth count we can have, the greater torque multiplication, and usually the stronger our diff is, the more torque it can handle. We will have a cover to access the differential assembly if it is an integral differential. And quite often we are going to have numbers stamped on that cover. If we don't have an integral diff and we have a removable center carrier, then you can usually have the tag attached to that. And the tag will give you pertinent information like the part number, the build code and the build date, but it will also give you the differential gear ratio. So on the top photo there, that really weird rusty rear diff, they're 373 rear gears, which means it's kind of right about the middle range while going towards the lower side of things for an average diff. Let's talk about the major design characteristics that we can have for different differentials. So they come in three kind of main design criteria: full floating, semi-floating, and three-quarter floating. Now, our full floating is going to be the heaviest duty and the strongest of the bunch. The axle shaft itself is not supported by the weight of the vehicle at all. Instead, a hub assembly is supported by two sets of tapered roller bearings that supports all of the vehicle's weight. So you can have a larger truck with one of these full floating axles, and you can take the axle shafts out of it before with the wheels not right on there. And you don't even have to take the wheels off. You don't have to lift it up or anything. Now, the benefit to that is we have 100% of the torque going to the axle shaft. It's very, very robust and strong and can withstand a lot of weight, especially lateral weight. The downside is, though, is the hub assembly is very large and usually sticks through the wheel quite a bit. So we tend to not see these on smaller vehicles or at all on smaller vehicles because of how heavy the differential is. The weight is a really, really big key factor. The unsprung weight and the amount of force involved in even getting this system to rotate down the road is too great for most vehicles to be able to handle, so we only see it for larger trucks. Most rear drive axles are going to be semi-floating. Now, semi-floating indicates that it is supporting the vehicle's weight, and we have the vehicle's weight supported by a outer wheel bearing, and then inside of the differential, it's supported by the side gear itself. These are what you're going to commonly find on most road-going vehicles. It's not necessarily like, you know, a light duty only type thing. It is much cheaper and it is a lot easier to operate these style differentials. You can have much more wheel options. You have less unsprung weight, so the vehicle's not as unstable and doesn't have to have larger brakes or different spring rate to be able to accommodate for that. Semi-floating rear axles are also far greater in reducing rolling resistance, which makes the differential overall more fuel efficient. You're able to deliver more power and more fuel efficient. You're able to, have that vehicle be much more well-rounded for what day-to-day operations would be. The last design is three-quarter floating axle. You don't see a ton of these. There are some older vehicles that have these, older Land Rovers, older Ford Model A's had these. And that is where we do have a semi-supported differential by the differential carrier, but the axle shaft is also supported partially by a hub bearing. Now, these are like medium duty type applications. I know the book states that it's more heavy duty than semi-floating, and that is the case, but not by much. You can make a semi-floating axle shaft pretty strong just the way that it is. Now, these axles are going to be held in with a flange. This flange is going to bolt the semi-floating axle to the end of the axle tube, or we're not going to have a flange, and instead, we're going to have a C-clip that locates it inside of the carrier assembly. Either way, the bearings that are supporting either a full floating, three-quarter floating, or a semi-floating axle have to have lubrication. They're going to be lubricated by the gear oil in the differential as it goes down the axle tube. Over time, because these axle seals are where the brakes are with expansion and contraction with heat, dirt and debris getting caught up while the vehicle's spinning or going through different off-road scenarios, you can have these axle seals fail. It will leak gear oil or axle fluid down onto the parking brakes or the actual brakes if it is a drum vehicle, and then out down onto the wheel itself. And oftentimes it's going to be a little bit of debris or something's gotten in between the seal, or the seal's dry rotted due to excessive heat cracking. Now, for these seals to not leak inadvertently because the system is overfilled, following the proper differential level is really important, and this does require you to look at service information. Oftentimes, it's always thought that the differential fluid level should be right at the very bottom of the fill plug or the bottom of the threads. And you want to double check that because you can be overfilling the diff by a fair amount. And that causes the fluid to cavitate. When the fluid cavitates, it cannot lubricate. It can't be a barrier between metal on metal contact. And it ultimately causes the vehicle to have a differential that goes out prematurely. Now, other areas that we can get fluid loss, the axle seals are very common. The front pinion seal is also another very common one, where the companion flange or input yoke to the differential is located on the pinion itself. That will have a seal. Again, anytime we have a dynamic seal, those can be an area for a leak. We can also have a leak from the vent, the cover, or the axle tubes as well, although those are a little bit less likely. One thing to watch out for with any of these dynamic seals is these rubber seals will cut into the hardened shafts. As we can see here with this axle shaft, you can see a line forming right here where the seal has actually worn a small groove on that axle shaft. If that's the case, you oftentimes have to replace the entire axle assembly because you can't really add material there. You can, but it then will change the heat treating of that end of the axle shaft to where you eventually can cause cracks. Now, if you leave it alone, that will cause a greater fluid leak, and that therefore can cause the entire differential to fail prematurely. Differentials can have a bunch of different ways that they can fail, but well and above the most common failure is going to be NVH, or noise, harshness, and vibration. You will hear a differential far before you have any issues where it locks up. Now, I have had them where they lock up with the pinion gear. The companion flange bolt or nut actually falls out, and the pinion gear gets jammed into the carrier assembly, and vehicle's not going to roll anymore. But it will talk to you way before that. Oftentimes, we can have the issue where a bearing starts to whine or make noise, but we can also have to where the ring and pinion gears, because the backlash is not correct, that causes chatter or singing as well. Now, the noise will change usually with XL and decel, as well as turning left and turning right. And so we are going to have to try to kind of pinpoint that down when we do have a differential that is making noise. Oftentimes, an inspection of the components can reveal worn out components or irregular wear. As we can see here with this side gear, this portion of the side gear assembly was chattering against the pinion shaft gears, and a piece of the tooth has been knocked off, and that will cause a popping noise heard when making tight corners at slow speeds, and it will be really concerning to the customer to hear. Being able to see that, you can see that that's the issue. Now, we do need to go through and make sure that the proper shims are being used for the side gears against the side pinion gears, and that the issue is corrected in setup. But excessive knocking can be caused by a worn out diff, just with it failing with natural causes. We can also have where the limited slip causes it to shatter because of a lack of friction compound in the gear oil. We can also have to where the differential pinion shaft, like this one right here, is chattering, where the axle is contacting it regularly or crashing into it, and that can cause excessive wear and vibration as well. But more often than not, it's usually going to be water intrusion that causes a differential to go bad, or overuse. And differentials, just like any component, it's a mechanical component, they're going to wear out over time, and it is your job as a mechanic to get it back into service. Now, when we're looking at diagnosing any type of concern, you obviously want to verify it first. You want to test drive the vehicle and make sure that there is nothing, or that it can be duplicated first off, but that there's nothing else that it couldn't not be. Rear differentials can be somewhat tricky to diagnose for NVH. And the reason being is if you have a large hollow aluminum drive shaft, it can transfer the noise up to the transmission, and it can give the sense that the transmission's making noise instead of the actual rear differential. But we do want to try to use steel veneers or drive with a passenger in the back to be able to pinpoint when the differential is making noise. Now, when we do have a differential noise, we want to try to pay attention to when it's making that noise. Is it making the noise when we're accelerating or decelerating? Is that bearing noise due to poor setup, or is it going to be due to a lack of lubrication? So checking for leaks is going to be a big one. Is it going to be we use the wrong gear oil? Do we have a plugged breather, and that's causing a buildup of pressure inside of that and causing the fluid to be pushed away from the actual gears themselves? You have to be able to figure that out. Now, there's not a scan tool that you can plug in to tell you that. You actually have to physically, put hands on the differential to make sure that you're checking that. Now, during your inspection of the differential, there's going to be some components that are wear items that cannot be reused, like the crush collar, which provides bearing preload for the pinion gear. But we also want to make sure we're keeping track of any of the shims that come out so that we can get them back in the same order. At a minimum, it's for reference. If we have to reset the diff up and we have to reshim it, then that's going to be the case. But we can at least get into the ballpark with having the old shims in place to where you might need to just do some small, slight tweaks here and there to get everything to have the proper bearing preload or the proper amount of tension on the bearing and the correct backlash. It's also good practice when we're ever overhauling a diff to always replace all of the bearings. You're in there anyways, you might as well, and the bearings all fit with an interference fit against the components. So you typically damage the bearings if you're removing the pinion gear and trying to save those, they get damaged, or if you're removing the carrier assembly, and those will get damaged trying to press those off. And the bearings aren't terribly expensive, and you can get new ones very easily. Now, the first step with tearing a differential down is verifying all of the initial measurements. You're going to verify gear backlash. You're going to verify the tooth pattern, and it's not a bad idea to measure the preload. That way, you know where you're starting at, and you can see that. Oh yeah, my backlash is way too excessive, and that's due to a lack of lubrication. The gears contacting each other and wearing themselves out. Or it can be a situation that the differential wasn't set up initially correctly, and that's what's causing a fair amount of noise. Now, when we have the differential and we're inspecting it, it's important to make sure that we have the ability to get the carrier in and out. On the threaded collar design differentials, those are easy. You just retract the collars. You do lose your backlash and your preload of the bearings, but you'll be able to get the differential carrier out very easily. For shimmed differentials, you will have to use the component or tool that I have photoed on the lower left of the screen there. And that is a case spreader. This is the most barbaric tool you can possibly use. Effectively, you're bolting this to the transmission case, and then you're spreading the case apart. Now, you need to be very careful. These cases are made of cast iron, and if you spread them too far, they will crack, and it will not allow you to be able to hold fluid in the diff anymore. The other thing that you need to be conscientious of this with is typically when you're rebuilding the diff, you're going to be rebuilding it in the vehicle. The two photos that are photoed here are not representatory of how a mechanic actually works on a differential. More often than not, what we're doing is we are repairing it inside of the vehicle itself. This case spreader needs to be chained to the diff. I have had where they've come loose and they drop, and that is not something you want falling on your foot or on any other portion of your body. So you put a safety chain around it. Now this one is bolted up with 6 bolts, so it shouldn't drop loose, but even removing it or installing it, you do need to take extra care to not have it fall on you. Now, other areas that we need to make sure that we're paying attention to is gear depth. The way that we're checking that is we can't manipulate the carrier assembly. It's set on bearing races and it's not going anywhere. But our pinion gear itself can have a specific depth. So we will have a shim that will allow for that. I have found in most all the differentials I've ever overhauled, you are just going to default to using the shim that came from the factory with it. And you don't really have to worry about depth, but you use a special tool known as a scooter block, which is photoed here, to measure the correct depth that you can get the pinion correctly oriented with our side carrier. And like I said, I'm not even going to show you guys how to do this in class because it's going to be so rare that you're going to do it. It's probably, I would be willing to bet most of you will never do this in your career. If you're doing diffs day in and day out, then you will be. But even then, you still default to what the original shim that came in the diff was. Now, one thing that we do want to make sure that we have an understanding of is all of the bearings inside of these differentials are going to be tapered roller bearings, and they do have to have a preload specification and placed onto them. Now, our pinion gear is going to have a crush washer. This crush washer, which the mechanic has their index finger on, is not reusable. You have to replace it every time with a new one. And it will require you to crush down, and it does take quite a bit of force. In the best case scenario, you're hitting it with an impact gun, and you're a little bit at a time, and you're measuring the bearing preload or the breakaway torque with a turning torque wrench. In cases where it's a little bit bigger, you are having to use, breaker bars, and it can be fairly cumbersome. But once the bearings, the inner and outer bearing is installed, and the new seal is installed, and the companion flange is installed, you will torque the differential nut to a set spec, and then you will begin to turn it to get that preload measurement. Now, what this is doing is this turning torque wrench measures the breakaway effort that it takes to start rotating the bearing. So there's going to be a specification in the factory service manual. Usually, on average, it's going to be anywhere between 17 to 30 inch-pounds of breakaway torque to start to rotate this. Too little, the gears are going to chatter. Too great, they're going to bind and it won't rotate. So you really need to find that happy median in the middle there. Now, a couple things I want to touch on with overhauling a differential in terms of installing the carrier is the caps that mount the carrier in place, regardless if it's an integral or whether or not it's a removable style carrier. Those do require them to be oriented in the correct position, up and down and left and right. I like to mark them. So mark them with a Sharpie or a paint pen so that you don't get them backwards. But you're going to set the initial backlash. If it is a threaded collar design, you follow the service info. Normally it requires you to turn it a couple turns in and to torque up, and then you take your backlash measurement. If it is a shim differential, you start with the shims that came out of it, and then you work your way from there. Measuring backlash, you're going to use a dial indicator, and you're going to measure how much free play there is on the ring gear with the pinion gear held. And you're going to measure effectively the amount of movement left and right, the little click you're going to have in and out. And you're going to try to get that to within the factory specification. Now, the factory specification on most differentials is going to be anywhere between 2 thousandths of an inch to 8 thousandths of an inch. So not a lot. So you're not going to just, yeah, that feels about right. You actually need to put a gauge on it to double check. Now, if it is found that our differential has too little of backlash, then what we're going to need to do is we're going to put a shim or move the adjuster that is on the far side of the teeth of the ring gear. So in this case, it would be on the left side. We would change the shim out to a larger shim while removing an equal amount of shim on the right side, or we would be turning in the adjuster on the left side with an equal amount of turn out on the right side. And if it's too loose, we're wanting to push the gear towards the pinion gear, so we'd be adding material to the right and removing it from the left. Now, one of the other things that's going to be really important is checking gear pattern. The contact pattern between our ring and pinion gear is going to be really important to allow for them to live a very long life and be usable for a long period of time, but also to run quietly. Differentials can be very, very loud. So it is going to be important to make sure that we are checking both the drive and coast side of our drive gears. Now, the drive side is when we have torque applied, that will be pushing on one end of the teeth or one side of the teeth. When we release the throttle and we are coasting down, we are not applying torque, and that will then contact the back side of the teeth. And it's important to make sure that we have good, proper teeth pattern on both of those. Now, you can get a chart like this, and this is just a generalized chart that kind of can help you with getting the gear pattern to be correct. And there's one for the drive side and one for the coast side. So you can see if we're 3 photos down and we have an issue where the ring gear backlash is correct, but the pinion depth is not, that will require, that will show that the teeth are wearing a little bit too far on one end. So this will help you kind of, nail down what you need to change to get that gear pattern back in the right area. Now, you can use a marking compound. There's Dicam, there's Prussian blue, there's the liquid lead yellow stuff like this. Personally, I use white lithium grease because it's in the shop, it's cheap, it doesn't dry out, and you can do a very good job of checking your gear pattern. But you're going to paint this onto a couple gear teeth. You're then going to under load rotate the differential a couple full rotations. And you apply tension to the carrier so that it can simulate like it would be on the road surface. And then you inspect how the paint or in the case of what I use, the white lithium grease gets worn away on the gear teeth. Is it where you need to be in that ideal, down the center, in the middle, not too low, not too high, and not in a position where it's going to make any noise? Or do I have to make an adjustment from there? If you do have to make an adjustment, you clean the grease or the paint off, and then you redo the process again to verify that you have gotten everything within the correct tolerance. Now, if you are having to do shims, they do have a shim chart. Oftentimes, vehicles that do have shims, you're looking at like there being like hundreds of shims that you have to select. It's not that big of a deal. At my dealership, before we ended up having the bucket of shims, we had a baseball card album. That's what they had in parts. The bucket O shims that we use for measurement in here, that came about because of extra shims that were ordered, and so I and a bunch of the other mechanics would just kind of toss them in that bucket. And it was really helpful because that is one of the parts that I did not feel bad hoarding, because there'd be situations where parts would not have the shim to be able to get the differential finished. I didn't want to wait a day or two for just a differential shim. And we were able to get a customer's vehicle back on the road very, very quickly because we had those shims. Now, none of them are used. They're all new, but it was one of those things that it was worth keeping. Now, to kind of wrap things up, if the differential does have issues, we will have a concern with the differential eventually failing. When differentials fail, they tend to take most of the components out with them. So we can see here, this is a failed ring and pinion set that will have sent metal into the planet carrier itself, meaning that that has to be replaced. And so all the bearings, the planet carrier, the pinion gear, and all of the seals will have to be replaced. Really, only the housing is the only thing that does not get replaced during this type of failure. Now, it is important to always refer to service information. Never memorize any of the specs for torque or for preload or for bearing clearances. Always make sure we're referring to service information. Therefore, we can get the differential overhauled correctly every single time. Now, I am going to go through and do a big demo on doing this in class on how to overhaul a diff. I cut a lot of slides out of this lecture to try to save time and keep you guys attentively listening, but you can refer back to them if you want to see some of the step-by-step processes. If you stuck around to the end of the lecture, I appreciate you getting this far, and I will see you in the next one.